that's the integration. We just have it. Now I will do this, I will call it sine. Alright, well, so here we have sine equals xi minus x divided by h. Alright, so, and here we have a dx, and now we have a new variable, so this infinitesimal should change. So, here we take a derivative of, so d sine equals minus 1 over h dx, which means dx is minus h d sine. So that was sort of, I'm just repeating it. The question, the answer to the question will come now. Okay. Now let's see. So here x has bounds. So it is minus infinity, and then, I shouldn't write equal, because it can be, just for notational purposes, and it's not like that. Okay? So when x is minus infinity, then what is phi?
Infinity. H.
X is minus
One.
infinity?
One
So that's a
over
very big negative number. What will this be?
infinity. Because minus of
No,
minus
that's minus.
of minus.
So
So
that will be a very big positive number.
mm. Mm.
And then let's look at that. When x is plus infinity, then what is a very big positive number? And what happens to phi? It will be a very big negative number.
Mm.
Good. Now let's go on with the integration. And with the integration, so when x is minus infinity, and phi is plus infinity. And when x is plus infinity,
Minus.
and psi is minus. Now comes the I as it is. Minus 1/2. Smaller than, this equal psi. Smaller than 1/2. Alright.
Mm.
And then the x became minus h d psi. Well, I mean, there was 1 over h here. Alright. Now, so h with h cancel. This became minus integration, what is minus, we get to here. I minus 1/2, smaller than psi, smaller than 1/2, d psi. Now I have a minus, so it is minus this area, so it's from minus infinity, plus infinity to minus infinity. And well, that is equal to minus infinity, so swap the order of integration. Instead of going from minus infinity to plus infinity, so I can go from plus to minus, then swap the signs. Right? Then will be I of minus 1/2 psi and 1/2 d psi, which is 1. Right? So as the argument.
Mm.
It has a measure of 1. Can I use your copy? So this is the PDF. Well, now the question is that, well, is it actually, well, I mean, that's sort of what we have, right? So that was the histogram so far, right? So because it's jagged, right? So, all right, so histogram is, right? So it's a step function. So now if I look at this, right? So the very fundamental part that made this a PDF is this. It's a localization that we had. Sort of that you had the H, and H was a band, and then in this band then you were looking how many observations you had, right? So it looks like that maybe I can take this step function and then replace it with some other function, whatever else, which is positive, and the area below that is 1, then I'm left with some other way of estimating the PDF. Right? That is what we do, right? So this indicator function, we can replace it with any positive function k, which which is a kernel that satisfies this, that the area below that is 1. That's why we use Gaussian in the kernel, because the area below that is 1. We could use any other function. We could use triangle, and we also make it in such a way that the area is 1. Alright. And then we will be happy with it. Alright. Well, I mean, this is actually also important to keep in mind that this kernel function that we have here, because the area below that is 1, then necessarily it should be in such a way that the tails are very thin. Right? The minus infinity is 0, and the plus infinity is also 0. It must. It can't be non-zero. Because if it is, then the area will not be 1. It will be bounded. Alright? It must be in such a way that we have it like so. So this condition indeed embeds these. We don't need to escape them, but we have them always in the back of our mind, and that's important. Why? Because the further you go from the center, the smaller the weights become, and that is what we want. So we want them to go off. We want the observations which are far away from where we are not to have any effect because they're not important. That's too far in the future, that's too big, too small, too far away from where we are. So these weights should actually vanish. The smaller, the smaller. The further away you go from 0. So that's an important indeed assumption. Well, I mean, with this kernel, all right. So this is also satisfied because here you have this 0. So right away becomes after minus 1/2 0, and right away after plus 1/2 also becomes 0. With the Epanechnikov also, all right. So this is like this. All right? So it's like lambda, like a triangle. It's some number, and afterwards just vanishes, it goes off. All right? But of course, we do this triangle in such a way that this area is 1. Okay? That's important to keep in mind. So this K is generally referred to a kernel function, as we basically talked the other day. Right? So that's the kernel that we have here. All right. Well, I mean, as I said, so we did actually a little bit of exercises. So here, oftentimes we actually use symmetric kernels. Right? So for example, let's say if you have for example, with the sine function, when we wanted to estimate, say, the value of the function at goes from 0 to 5. Let's say at 5, then we were looking at the values to the right and left, both sides. So this is actually because we have a symmetric kernel. Right? Sometimes you may wish to have a one-sided or asymmetric kernel. Right? For example, let's say there may be the case where well, that's a project actually I'm doing now with what is these centers that they take blood and distribute it to people who need it? The blood centers in Australia. So I'm actually estimating for them the distribution of the blood demand. So the demand can be negative. Right. So the distribution is something like, there are many people who don't need or who really need, but then there are some that they need less, so sort of the distribution looks like so. So if I want to estimate the data, sort of the distribution at this point, then I don't have negative values. So I need a one-sided kernel. That needs to be chopped. So it looks at positive values. In finance, it's also used. But I mean, let's say you want to estimate, say, the variance, then you should be backwards looking. So your kernel should look back, can look ahead. Can be symmetric. Must be 1, yes. Must be 1, must be positive. And the tail should go off.
So can I ask again about the simulation of sigma functions?
Yes.
So if we want to do, I think like in the middle, we have both data on the left and data on the right.
Yeah.
But what if like we're trying to estimate using the data from today or yesterday? Like, it's really like we have little from the right.
Very nice question, I really like it. So here when we have the sine function, right, so it looks like so was our estimation, it was like so, right? Yeah. So that was what the estimation would be. But this is an estimation, right? Okay. And every estimation comes with a risk. It's random. So random, right? And then always whenever you had estimates, you were also, you had point estimates, and you also learned how to put together confidence bands, which are the interval estimates. Interval estimates here will be wide, and there, when closer to the center, become a little bit sort of, will look like so.
Mm.
So here will be a bit wider. In the beginning, they are big. At the changing points, also big. You understand why? It's sort of when sort of the function goes up and then comes down, then you get panic. Right? So the function is going up, and now it comes down. Right? So sort of things become a little problematic. Because when you estimate those points of the function, then you estimate values which are smaller to the left and smaller to the right. So sort of it's a little an issue. Right? So then the confidence band and modes generally are higher or sort of bigger. So are in the beginning, where you don't have actually good data. Right? So that's actually a general rule. For example, let's say in OLS, right? So let's say you have some data like so, and then you have a linear regression. Then oftentimes if you do the confidence bands here, then you see them for the fitted values, it would look like so. You have seen them potentially. There are generally in books here and there, such pictures. And in the end, where you have few observations, or in the beginning, when you have few observations, then the confidence bands become big. Right? What does it mean? It means that the predictions in the middle are okay-ish, or they have a good quality compared to the beginning or the end. So for forecasting, what generally says you can, or sort of prediction, you cannot predict, say, for here. For example, let's say if you have data on newborn weights and the smoking behavior of mamas, right? Then you can use the smoking behavior of fathers, right? You can, that has an effect, but that is sort of mother's smoking behavior has a bigger effect. So you cannot actually, that is so validity of the sample, in sample you are valid, here you are very much in sample, here you are almost in. So it's sort of at the ridge. So here you have big confidence bands and here too. This is also the case. Right? And indeed the question that you have is very beautiful because you say, hey, what is happening here? So maybe we should use a kernel which is one-sided here.
Yeah.
Maybe. I'm not saying no. Maybe you can try. Yeah. So you can try and then see if I use a one-sided kernel in the beginning and in the very end, then what happens? But actually, you should also always think, do I need it? Do I need the beginning and the end? Maybe not. So, well, indeed, oftentimes what matters is, I mean, in economics is the derivative of n. So you need the marginal effects, which we learn how to get. Very nice lecture. All right, so you may use asymmetric kernels. Sometimes you may use negative ones. So one can tweak them. So the assumptions are assumptions. You can change them as you want for a certain book. Okay? But first you have to know the assumptions. And then once you know them, then you can tweak them. So I will do that all the time. Right? So change things that are in paper. That's how things work. But let's actually look at the assumptions. Right? So as I said, they're important to know. And there are general assumptions that actually this stuff works. Right? So but you can actually estimate this PDF using these methods as we have in this curve. So assumption number one is that the observations are IID, independently identically distributed. Right? This assumption can be relaxed. Right? Early 2000s, then there came some papers, theoretically, econometric theory, that actually relaxed this IRD assumption. We can now mark it in different series, which means that, well, I mean, as long as the dependence is, alpha mixing processes. Alright. So let's say for R models, then it works. Alright, so a stationary R model. But we work with the IRD now because that makes things tricky. Generalization always is possible. And then K is symmetric around 0, is positive. Alright. And then the area below that is 1. So that is what I told you. Assumption number 3 is this. This is e2, e to the power of 2, right? For example, let's say if I have a Gaussian kernel, then this is the second mode, right? So we call it mu2. It's also non-zero, right? So this can't be 0. It should be a non-zero. So it means that you can, if you choose a kernel which is negative, then you should choose it in such a way that, because if it is positive, then this will definitely be non-zero. If you have a positive kernel. But if you have a negative kernel, or sometimes it becomes negative, it's possible, then this should be non-zero. Well, kernel to the power of 2 should be bounded. So for example, let's say if you take a Gaussian kernel to the power of 2, take an integral, then it should be a bounded, or it is bounded. Alright, so that's a bounded indeed quantity. So now let's actually talk about the density that we want to estimate. For example, this is the density I want to estimate. So we need the second derivative of this, so that's the curvature, to be continuous in the neighborhood of x. Right? So that means that if you have a density which is, for example, let's say you have data which have like so. Alright. Well, let's say this is the distribution of donations. Many people don't donate. 0. They don't donate. They don't care. They tell you, why don't you donate? Say you don't want to donate. That's it. Alright. But then there are some other people who donate. Some value. But then very few donate, say, more than 1,000. Alright. Well, sort of that's the density. So you have a point and some other point. So people are either here or from this. Right? That's not a continuous density. Right? You can estimate this density not at 0, away from 0, where you have continuity in the curvature. Right? So that's a continuous function. Right? That's important to. This is by the way called Bonchik in econometrics. Maybe you want to check for yourself. That's actually a behavior very often seen here. So these were a little bit of assumptions here. Now let's look at the bandwidth. All right. Indeed, the bandwidth should be a function of the sample size, and it should be in such a way that when you have a bigger and bigger sample, then the bandwidth becomes smaller and smaller. Right? So to speak, when you put together a histogram, if you have many observations, then you can choose the bits very small. If you have very few, then you can't choose it very small because nothing will be big. Right? The B is big, if the sample size is large. The bits or the bandwidth here should be chosen as smaller. You could be able to choose it as smaller. And that means that we require h to be a function of n in such a way that when the sample size grows, this h becomes small. Alright? That's another assumption. And then assumption number 5 actually says that h times n should be big. Alright? Right. For example, let's say you choose h to be n to the power of minus 1/5. Yeah, that's an example. So it means that when the sample size grows bigger, h becomes smaller. But at the same time, h times n, it is n to the power of minus 1/5 times n, which is n to the power of plus 4/5, and that diverges, because that's n to the power of a positive number. You can choose n small, or well, you can choose as big as you wish, right? As long as it vanishes, and at the same time, it sort of goes to zero, not slower than how n goes to infinity. So that's sort of the important. So these are the assumptions. So A should be chosen in such a way, theoretically. Of course, we did actually a choice based on the cross validations. We didn't care about this stuff. All right? So in practice, we may actually take a different sort of approach, but that is what we need for the theory. All right. So now let's see how does this actually work. Why does it work? How big the bias is. Right. So I will do the theory here so that you understand what I wrote red on the board, the bias variance trade-off, so that you understand it. That's a very important concept in machine learning. And nowadays you should actually know what is this variance bias trade-off properly. So I will do it. It will be a bit of it will be a bit involved, but you will understand. I will take it step by step so that you know. All right, let's see how this function looks like, the estimator. So that was 1 over NH. So here we have the indicator function, and now we change it with the kernel. Right? And let's actually rewrite this a little bit easier. So this kernel divided by H, which is this, let's call it WI. That's okay. So then we have an average. So that's a simple average. And because that's an average, then you know how to estimate or sort of how to analyze its behavior using law of large numbers. Because law of large numbers was a method for actually talking about the averages. Right? And this is an average. We can actually check whether this is an average that converges somewhere or not. Right? Let's see. Well, the first thing that we can do is to calculate the expected value of this. Let me again do the calculations myself, all right? So that you understand. So let's have this in front of us, and calculate the expected value of this guy, all right? Remember, so that's an estimator. And whenever you have an estimator, that's a point estimate. Then you have to do two things. You calculate its expected value so that you know how big the bias is. So that's number one. And then you need to calculate the variance of it so that you see how precise it is. So these are the two very important indeed aspects. The estimate, the calculate, so to calculate the expected value so that we know how the bias looks like, is it big, is it small, or is it zero? And we also need the variance so that we see how precise our estimation. Because if the variance is big, then there's no good one. But maybe in the way of calculating the bias and variance, maybe we will understand how to reduce them. Because we see them. If you have them in front of you, you say, aha, so I can make it small using this and that method. Right, so let's see how the expected value looks like. All right. You're the only one who Alright. So here we have WI. We need 1 over HK of xi minus x divided by h. So you have to remember x is a random variable. Xi is a draw, a random. Okay? Other variable. X is a point where we calculate the expected value. So that's fixed, that's a point. And xi is a random sample. So we are taking the expected values with respect to xi, not x. X is a fixed number. That's a point at which we want to estimate the median. Xi, on the other hand, is one random draw from the distribution. All right. in here, f hat at x is 1 over n summation of this w over r. So if I want to calculate the expected value of this, I can simply use my expected value operator. The expected value of fh at x is 1 over n summation I expected value of w. Right? So that's the linear operator. 1 over n comes out, and we did the other day. And so let's calculate this expected value. Expected value of wi is 1 over h. Expected value of k, xi minus x divided by h. Right? Which is 1 over h integration from minus infinity to infinity k of xi minus x divided by h dxi. Right? Well, let's do the change of variable. As we did just now. Okay. So this we can call, what do you want? U?
So that's the second letter of your name.
And then let's see. So d xi is equal to h d. Right? So you are fine? You see.
the
Yours. So that's sort of what we have. When xi is negative, then this is also negative, and it's positive, then it's positive.
positive.
So then this is like, so 1 over h with this h cancels. So we are left with integration from minus infinity to plus infinity of k u d. And this is by assumption. Because we wanted the kernel to have an area below it. That is what we assume. Good. So, the expected value is oh, but wait a moment, this is not h, this is n. What did I do? Because my h is different from n.
H, yeah.
I am a mess. And nobody told me anything. That's an expected value. So the expected value of a function, that
Yeah.
function times the PDF for a bunch of PDF. So let's continue, that's okay. So that is what we have as u, alright? And this is xi, and this is also xi. Good. Alright, that's better. Let's now, well, I mean, do the change of variable, I'm sorry for that. So here we have u equals xi minus x divided by h. Alright. So what does it mean? It means that xi is equal to h times u. This goes to the other side plus x. Right, so that's sort of what we have. xi is this. So that's x plus h. You are happy? So now let's look at d xi. It is h d. Now we can plug in. So then here we have integration. Then u is positive, then this is positive, so this is minus infinity plus infinity. K u times f of x plus h u d. Right, so that's the expected value of w. Right. Maybe let's call this ui, because indeed this is an I. that's for the eye field observation. Yeah? Good. Now what do we do with this? Right? Well, this is actually a little bit of a problem. Right? So, well, I mean, the expected value of WI is this. Yeah? And that's the same because we have an IID expected value, then this is actually the same for all of the observations. All of them have the same density, the same indeed behavior. Now let's look at the expected value here. So expected value of f of x becomes, so that's an n, 1 over n. So here we have 1 over n summation over these guys n times. They're all the same. Then this I can write as integration, so 1 over n summation, well, n times that, minus infinity to infinity. Let me just drop the I, because they're all the same. kd, f of x plus hu d. Alright. So I drop the I. Because they're all the same, they're IID. Okay. So now we have some 15 minutes more or less, and I want that you do a bit of work. So that's the expected value. Kd times this. All right. Let's say we have a function gx. Okay? So I need the Taylor's expansion of g at 0. And let's sort of say a smooth function of any order you wish. So I want that to do that somewhat for all of you together. And then the Taylor expansion of that function. Well, that's another function, right? So I just wanted to remember Taylor, and then I will come back. All right. You can do that.
I hope you remember.
I will help you, of course. So I will come with me. Very good. Beautiful. Very nice. Excellent. And then it goes on and on. Thank you very much. So you remember, right? So that's the Taylor expansion of this function at 0. So now let's do it here. Okay. That's very good. So now let's define GU to be GH to be f of x plus HU. So now can you write the Taylor expansion of this at H0? Well, that will be the same as you wrote there. That will be G0 plus G prime at 0 times H plus G double prime at 0 variable as you had it there.
Mm.
So what is G0?
fx.
Yes. That will be f of x. And G prime. You should use the chain rule.
U.
Yes. So the derivative of this with respect to h is u. Very good. Times
It's minus. It's U. It's U.
u squared. So here we need this is let's look at the so g prime of h. Well, the derivative is with respect to u f prime x plus h right?
Yes.
So the derivative is minus the second derivative and this with respect to now tell me or whoever someone. Yes.
Second derivative.
So then exactly so then
U
it's
squared.
square.
U square. F. Oh yeah. X.
Plus some other terms, right? Plus some other terms which are of order h to the power of 3. Yeah, you agree with that? They are not actually order integral, they are very small values, right? So let's write them all h2. Right? So they are small. There are quantities which are smaller than h squared. So I use little o for it. Okay. Let's plug this in here. Okay? So this Taylor expansion, I will plug in this expression. So this is Ku times the first term. Plus Ku, well there is a U, Ku, f prime of x, h du plus what u squared f prime of double prime of x and h squared d plus some other term. Let's call it remainder as a function of h. Alright? I don't care what it is. Some remainder. But that's this little, well, that's the rest of, so, yes.
One over n form the integral term.
No, but that cancels. Now let's go back. So because here we have summation of n of this. So that will be n times that divided by n. Equals of. But are you happy with this? You can follow this plugging in. Yeah, so just plug it in. Now I want that you tell me something about these terms. Right, so this is f of x, so it comes out. Yeah. So f of x comes here, and then we will have integration from k to d, which is 1. The area below the kernel is 1. So this is, the first term is f of x plus. What about this? This is actually comes out of the integration. Right? What is this integral? Change is symmetry.
It's so patient.
Well, that's exact. So expected value of u with respect to this curve. That's a symmetric current. How much would this be? Is it
Zero.
Zero, no. This rotation would be zero.
Well, I mean, this, what will this happen? I don't know. So that will be 1 over h squared. Here we have 1/2 h squared, the second derivative of x, plus integration u squared k u d plus the remainder. So now this I can leave out. Here then we have expected value of f hat of x is equal to the true parameter. Let's take it to the other side so that it becomes the bias. Is equal to 1/2 of h squared, the second derivative of f of x. And this is like a second moment. This is like mu2. So that's the second one. Plus some remainder, which is all of h squared. Right? So that's a term which is smaller than this. Okay. So now, so this is the bias. Okay? So the bias of the estimator looks like that. What should you do so that the bias is small?
Increase the edge.
Sorry,
Increase the edge.
small,
Increase the edge.
decrease.
Increase.
Make
No,
it,
we can decrease.
make it smaller. Right? So if I make this smaller, then it becomes smaller. So now you should understand why a smaller h means a smaller bias. Right? So when h was a smaller, intuitively, I gave you the intuition. So we were actually focusing on more relevant data points, and it was making the more relevant data points means less bias. And that is the theoretical reason. Right? Well, we have it in the regression. In the m function, the expressions are similar. A bit of ups and downs, and you get something which h squared actually shows up. Right? So you see the order of the bias each h squared. It's a function of h, positively. Well, and then you remember in the assumptions that we require the second derivative to exist. Remember? Right? I wanted this to be there so that we can have the second derivative of the PDF. That was one of the assumptions. That's the reason. But if you don't have it, if it doesn't exist, then you could not have a neat expression for the bias. You wouldn't know how the bias looks like. But if the second derivative exists, then you can do the Taylor expansion as we did here, up to second order, and then you will have the bias. So that's one. And now you also, I want that you also pay attention to this zero that we actually told us. This is zero. Right? This became zero because we chose a symmetric kernel. Right? If we didn't have the symmetric kernel, then the order of the bias would have been h, which is bigger than h squared. Right? The same as you have h to be 0.1. Right? Then the order of bias, if you use a symmetric kernel, will become 0.01. So smaller, because we have a symmetric kernel. So, well, the symmetric kernels are interesting and people look at them because they have a smaller bias. Because this term, which we have here, just vanishes, just goes off. You don't have it. That's why people use symmetric kernels more often than asymmetric. Yeah, so that's the reason. That's the reason we have that assumption of using Gaussian, because it makes the bias automatically small. Right? So now you should actually think to yourself, so if the choice of kernel could make us have a smaller bias, right, then maybe we can tweak the kernel and then make this term equal to go off. Right? Right? So this term is actually coming from here. So if mu2 is 0, then this will also be off, and then you will have a smaller bias. You will actually, remember, so if I was doing the Taylor expansion one more, then you would have had h to the power of 3. Right? So it would have reduced the bias. And that means that, so that means that if I could choose a kernel that for that u is 0, the u squared k is also 0, then the bias will even become smaller because a higher order term in the data expansion will show up in the bias expression. Okay? But that would require the kernel to be negative. Okay? The bias reduction is possible if you sort of are willing that to choose a kernel which is not positive. Right? In such a way that this term also goes off, and then you will have a smaller bias. Right? So bias reduction is possible at the cost of choosing a negative kernel. Okay? Sometimes you do that. Yes.
What is that implementation meaning to?
Mu 2? Yeah. Sure. So that is mu index 2. This is here. Mu 2 is the integration of u squared over all the real numbers of k u d.
The second one.
I just wanted mu 2.
Before it's not a plus one, before the thing that you put in the square, that right before that integral, you have the plus.
Mà hết rồi. Thấy kỳ kỳ từ khúc đó.
I did it on purpose so that you pay attention. That's the usual joke all professors do when they make a mistake.
Chị cũng đang không hiểu tại sao chỗ đó dấu cộng. Bị khẩn lại từ lúc đó.
Good. So, choosing H is smaller means the bias is small. So now you have to understand what happens with the variance. Alright, so what will happen with the variance? Will the variance become smaller or bigger when H becomes, well, we know that if you choose H is smaller, the variance becomes larger, but we have to understand it. Right? So, just to see how it is. So, well, I mean, that's actually not a big deal. You can go and calculate the variance. So that's the second moment. Who cares? Right? You can do whatever. This key is that soon as you see it in front of you, and I will do the calculations for all the variables. I can't. Because time is all. But I can actually at least write the expressions, alright? So if I want the variance of this jump, the variance of that it of f hat and x, it is 1 over n squared summation over I of variance of w1. There is no covariances because we started with an IID sample. So if I was actually with a dependent sample, then I have to take care of the covariance too. But I would just do it IID so that it's a little bit less involved. And the point is that you understand the effect of H on that. And because this is IID, this variance is the same across all. Right? So let's maybe then calculate variance of one of them. And that is the H1 over H, K of xi minus x divided by h. Alright, so that's the variance of v. So then this h comes out. Alright.
Square.
Right? And becomes a square. H is squared. And then now we will have the variance of this curve. One of the bits. And now we have to do a little bit of inflation. And then we will get the variance. Maybe let's just stop here, have the lunch break. And then in the afternoon, in the beginning, then I will do this variance bias, the variance of the diagram. And you follow me for all of my mistakes. Everybody, please. And then afterwards, we do an implementation. So I have generated some data, they are online, and then you go find the curve.